Okay, so today we'll be discussing the natural bond orbital analysis. So, the natural bond orbital analysis is a method that converts the complicated quantum calculations into something that can be easily recognized by a chemist in terms of molecular orbitals. So, what does the NBO describe? The NBO describe bonds, lone pairs, hybridization, and donor acceptor orbitals. NBO is also responsible for the bonding orbitals, the antibonding orbitals, the lone pairs, and the core orbitals. Yes, you can see all this of your material in the NBO analysis. So I'm going to be sharing this material with you at the end of this video. So the next thing you want to do in order to start this analysis is have your log file or your output file of interest. So today we'll be working with this compound. So what you want to do first of all is open it with notepad, because your MBO analysis is carried out in the notepad, not in gas view this time. So what you want to do next is search, Control F, or you find, search for second, search down, find it. So you are at this table, second order perturbation theory analysis or Fock matrix in NBO basis. So basically this is how your NBO table should look like. I am going to be explaining all these parameters. You have the donor orbital, the acceptor orbital, you have the perturbation energy E square. This is supposed to be raised power of 2, but due to calculation it's always like this. Your perturbation energy, your energy difference, and your overlapping effect. So everything concerning these parameters is going to be mentioned in your document, this document. So let's get into this. To select specific interactions for your NBO analysis that you are going to be recording on your table in the process of extraction, you need to know which atoms are in contact, what is happening. So this same material, this same log file that is opened in notepad, we are going to open it in gas view. So we have it here in gas view. So this is what the compound looks like. So you have to understand the concept of your study first off. So the concept of this study is to absorb this drug called TCS on this surface. This surface is called graphitic carbon nitride. So we are absorbing a drug on this surface. So we are trying to study the efficacy or the efficiency of graphitic carbon nitride in the absorption of TCS. So to carry out NBO analysis, you have to know which atoms are in close contact. So we can see from this log file that this guy is looking, has a close distance with this. We also have this hydrogen atom with this in close distance. We also have this with this. We can also consider this and this just randomly. You don't really need to take notes, just know what is in close contact. So we should be expecting bonds between chlorine and nitrogen, hydrogen and carbon, chlorine and just chlorine and nitrogen. Yeah. So next you need to know what atoms are of common interest between your adsorbate and your adsorbent. So for graphitic carbon nitride, you can see that it is mainly made of carbon atoms, nitrogen atoms, and hydrogen atoms, while TCS is made of carbon atoms, hydrogen atoms, oxygen atoms, and chlorine atoms. So you see that the main difference between TCS and graphitic carbon nitride is nitrogen and chlorine. So that's where they have differences. So with these two, okay, nitrogen, chlorine, and oxygen, yes. So with these differences, we can easily differentiate both of them. So what you want to do next is go back to your notepad. Now on your notepad, you have to start scrolling. Scroll till you see favored interactions that you can select. Now, while scrolling, you would have to be very careful, because I think I've explained what BD means from the document. So let's go back to the document. So on the document we have BD1, BD2, and BD3. So BD1 is always transcribed as a sigma bond, and in chemistry we know that a sigma bond is a single bond, while BD2 and BD3 are known as pi bonds, because we know that BD2 represents a double bond while this represents a triple bond. So the same thing with the anti-bonding orbitals, but the anti-bonding orbitals now show that you have an asterisk attached to the orbitals. Then lone pairs, which are symbolized as small letter n, are represented as LP and LP asterisks, while core orbitals, which are not part of what we're supposed to select in terms of our donor acceptor interactions, are the core orbitals and the Riebeck orbitals. These are inner orbitals, and they are presumed to have high energy or very low negligible energy, so we ignore. So let's go back to our note file. So on our note file now, we're going to start checking. So we have carbon 1, nitrogen 23. Now you're going to see a label at the top within unit 1. So what the NBO calculation does is, if I scroll down for a very long time, I'm going to see from unit 1 to unit 2. I think I should scroll so you can see it. Going to be scrolling for hours depending on the complexity of your compounds. You would scroll for a very, very long time. So yeah, okay, so from this calculation I think we are lucky because some compounds are split into many units. So this compound wasn't split into many units, it has just one unit. That is very, very, very surprising. So since it has just one unit, which means everything is here. Now we've already known the difference in our compound, I mean between TCS and graphitic carbon nitride. So wherever we see chlorine, we'll know that TCS, where we see chlorine or oxygen, we'll know that TCS is interacting. Where we see nitrogen, we'll know that, oh, that's graphitic carbon nitride happening there. So we're going to start from the beginning. There's a lot of scrolling. Going to start from the beginning so I can explain. So you're going to start choosing interactions, favorable interactions. Now, for selecting interactions from the donor side, you can never select a donor orbital that has an anti-bonding, like an anti-bonding orbital in the donor orbital region. You can't, because you're going to see it definitely at some point. If you happen to see BD asterisk on your donor orbital, do not select it. It's not feasible. Yes, but if you happen to have BD, just bonding orbital, or lone pair orbitals on your donor side, you can select. But if you have BD asterisk or LP asterisk, do not select from your donor orbital. It's not feasible in chemistry, because the chemistry behind it is that your anti-bonding orbitals do not have the necessary electrons to donate. So why would they be in the donor orbital region? But you happen to see them in these calculations because these calculations are done by computer. So the computer is running a simulation to find every possible means of results that you can get. So as a human being, you are meant to sieve out the chaff. So you don't select interactions with anti-bonding orbitals on the donor side. Secondly, we don't select the ry, which is the Riebeck. They are all co-orbitals, ry and cr. I don't think we're going to see cr in this file. Ry and cr, we don't select them at all. Any interactions having ry and cr, we do not select. So starting now, let's start now. We are looking for favorable interactions. So let's start scrolling. Favorable interactions in terms of donor and acceptor orbitals, and also in terms of the perturbation energy. So we start. We have BD, keep scrolling. So now we come across this. So we have C1 N38, C3 N39. So this is just basically telling us that if you go back to check your um your gas view, where is C1? C1 N38 on the donor side, and then C3 N39. Where is C3? Look at C3 N39. So you can see the electrons are just moving on a straight line. So the bond between C1 N38 is giving electrons to C3 N39. So electrons just moved like this. Yes. So, and what we are looking for is electrons moving between C3N4, that's graphite carbon nitride, and TCS. So it is not what we are looking for. Yes, I didn't mean we were just studying C3N4 alone. We can select such interaction since the perturbation energy is also favorable, but we're not selecting that. So we keep scrolling till we find something that meets our expectation. So we are still seeing a lot of C3, C and N, basically telling us that this is the surface that we are looking at. So keep scrolling. So we now meet another one. Yes, look at this, and also look at this. Look at this now. We have BD2, C6 N36, C4 N35. Clearly looking at this, you know that this is still a charge transfer happening within graphite carbon nitride. But if you look at this now, you know that only oxygen is specific to TCS. So you have C6 N36, oxygen 65, hydrogen 66. So we can check it. Where is C6? Let's check it. Find C6. Oh god, this is C5, C6. Yes, C6 to N36, and this is oxygen 65, hydrogen 66. So you can see that we've gotten our very first interaction between our surface, graphite carbon nitride, and our adsorbate material, TCS. So that is a perfect interaction that we can record. So we are going to record this. So you would scroll through till you find as many as possible favorable interactions that you can find. So we are going to record this on our table. Now, how does your NBO table look like? How is it expected to look like? We are going to make a table down here for me to show you how your NBO table should look like. So we're going to insert a table. Yeah, insert a table. So as usual, your table is first going to have the name of your compound. The name of your compound. So the name of this compound is TCS C3N4. Yes, this is the compound we're working with. So you're going to have donor, a column for your donor, which is I is the donor. You're going to have the acceptor. the acceptor, which is J, you're going to have your second order perturbation energy. Second order perturbation energy. So you're going to have your energy difference, which is the energy difference between your donor and your acceptor orbital. So your energy difference is always the acceptor orbital, the energy of the acceptor orbital minus the energy of the donor orbital, and it is measured in atomic units. So you're going to have your coupling effect or your overlapping effect. So this is the measure of overlap between your donor and acceptor orbital. Basic chemistry um, terminology. So this is how your table looks like. So that's information we've gotten from our notes file. We're going to paste it here. So pasting it here, it's not going to look like this. You have to edit it properly. So you have BD2 C6 N36 on the donor side. So we have BD1 asterisk, oxygen 65, hydrogen 66 on the acceptor side, and then we have perturbation energy of 9.48, energy difference of 0.82, and overlapping effect of 0.081. So now for this, we are going to be changing everything. We are not leaving anything like this. Yes. So let me get the OBD2. I told you it is pi. So we're going to insert our, we're going to insert pi here. Yes, pi is for double or triple bond. So make sure you put your labels in subscript format. Yes, pi, and give a space, please. Don't let that happen. Yeah. So don't forget to put your labels in subscript. So this is for your donor region. Then your acceptor region, you have BD antibonding 1 in the bracket, which is a sigma bond. I don't have a sigma bond in my equations, so I'll just copy from this file and paste it. So this is a sigma bond, and adjust subscripts. So yeah. So I have my first interaction. For NBO, you can pick as many interactions as you want. Yes, depending on the concept of your work. So it depends on how many compounds you are also working with. If you're working with 10 compounds in a study, I'll advise you to pick one per compound, because you don't want to overload your work and you are going to still discuss your results, so you don't know how stressful it will be. But if you're working with one compound in your study, like let's say it's for a drug, or let's say it's for a corrosion study, it's it's good to pick as many interaction as possible, so we can still go further and search for another favorable interactions, probably between graphitic carbon nitride and maybe chlorine on the TCS material. So that's all for your NBO analysis. So this is how your table is presented. You can put as many interaction as you want. Then maybe you have other compounds, you just increase the number of columns and then put the next material that you're working with. That's how it's done.